we are going to look into quantum algorithms again, but this time we will be looking at the one which is the most impressive example, the Shor's factorization algorithm. This suggests that quantum mechanics allows factorization in polynomial time instead of the exponential time and could have a dramatic impact on the field of data security. Now, the reason why this is so amazing is if you can get factorization done in a time frame which is in polynomial as compared to the present exponential time dependent methods classically available, then it would mean that the data security, which is basically based on the idea of prime factorization with a large number, is going to have a lot of difficulty in maintaining security. So, that is why this particular problem is very interesting to look at. On one side, it also provides on the other side better ways of creating cryptography, because if you can do this kind of exponential benefit, then you can come up with better aspects of cryptography which can be applied. So, this has big advantage and understanding of the security issues. So, Shor, who is at the AT&T Bell Labs, came up with this idea in the once again in the 90s. So, so here is a quote from him. He said that if computers that you build are quantum, then spies of all factors will want them, our codes will all fail and they will read our email till we have crypto that is also quantum and down them all. So, basically it is an interesting idea that once you get the quantum advantage, then whoever gets it first has the upper hand, because if the spies get it, as he mentioned, they will be having all the benefit and our security goes. But on the other hand, once we have the quantum on our side also, then we can keep it so secure that once again nobody can read them. So, that is the reason of pursuing this particular concept of security through quantum aspects. So, he invented a quantum algorithm for efficiently finding the prime factors of large numbers. The classical factoring algorithms work in the order which is exponential in time, whereas the Shor's algorithm works in polynomial time, and therefore, it is so impressive, and that is exactly the utilizing the full power of the quantum, because that is expected when you do a quantum algorithm. The reason being that we all know that quantum subspace is exponential in size compared to the classical subspace. That is the reason why this should have happened all the time, and here is the first case where it was actually shown. So, the motivation is plenty. It is for factoring non-prime integers of n of L bits. Many polynomial time algorithms for integer multiplications are available, but there are no polynomial time algorithm for factoring, because it is like very easy to find the solution of two numbers which are being multiplied, which can be primes, but to be able to get the solution or the factorization of a large number into its primes is a hard problem. Quantum algorithms are faster than classical algorithms, that what we will show. Algorithm is based on quantum Fourier transform. So, this is one of the things which we will also learn as a part of this particular algorithm, where we will be learning about quantum Fourier transform. The runtime is the biggest advantage, as we have been discussing before. For a classical case, it is exponential, whereas in the quantum case it is polynomial. So, the exponential comes because I have a log sitting here and an exponential sitting here. This is the reason for our exponential. Okay. So, the Shor's algorithm shows in principle that a quantum computer is capable of factoring very large numbers in polynomial time, the algorithm is dependent on modular arithmetic principles, quantum parallelism and quantum Fourier transform. So, the first part, which is modular arithmetic, is essentially classical, there is nothing new in it. The quantum parallelism is the part which is quantum, and obviously the quantum Fourier transform is also the part which is quantum. So, the entire algorithm therefore has essentially parts, some of it remains classical as expected. So, the problem can be stated in such a way: given an odd composite number n, find an integer d, sorry, it should be strictly between 1 and n that divides n. The Shor's algorithm consists of mainly two parts: conversion of the problem of factoring to the problem of finding the period. This part can be implemented classically. So, this is the part which is the classical, as I mentioned. Second part is the part which is finding the period, which involves quantum Fourier transform, and this is the one which is responsible for the quantum speed up, and it utilizes quantum parallelism. So, for learning the first part, or for addressing the first part, which is classical, so in order to do the first part, which is classical, let us look at some number theoretic background. So, there exists a theorem in the number theoretic principle which says that if n is a prime number and there exists a solution x such that x squared is equal to 1 mod n and x is not equal to 1 mod n and x is not equal to minus 1 mod n, one of the greater common denominators of x minus 1 and x plus 1 and n is going to be a non-trivial factor of n. So, in terms of what the Shor's algorithm does is that it inputs the non-prime number n and it outputs the non-trivial factor of n. The reason why this term non-trivial is important is because 1 is always a factor of n. So, we are not really looking for such non-trivial factors as 1. Okay. So, in figurative sense, this is how it looks. We have the classical part of the algorithm for which we did all this theorem, and the quantum part of the algorithm which is going to do the orders finding problem. And the first part is going to reduce the factorization problem into a problem of order finding. So, it consists of 5 steps with only step 2 that requires the use of quantum computer. So, it is important to note this, because if you think that the quantum computer is going to always have every step quantum, that is not true. That is the reason why I am also stressing on this part, is the algorithms often would be, which are even key for quantum computations, would still might not need everything to have the machinery of quantum ideas. Regular classical concepts would still be very important in many cases. So, in this case, the first step is to choose a random integer m such that it is less than m and they are co-prime. Now, the second step is to use a quantum computer to determine the unknown period p of the function f of m n, we have already chosen m n, of x, which is equal to m to the power x mod of n. So, the quantum computer is going to determine the period of this function, and finally, in step 3, if the period is an odd integer, we go back to step 1, but if the period is an even function, then we go to the next step. And the next step is that if p is even, then we are going to find this particular functional form, which is m to the power p by 2 minus 1, m to the power p by 2 plus 1, and find out how it sets up with respect to the mod n. And if m to the power p by 2 plus 1 0 mod n, then we can go back to step 1, because that essentially means that it is having a trivial solution. However, if m to the power p divided by 2 plus 1 is not equal to 0 mod n, then we go to step 5, which means that we are getting closer to the solution. So, what we have done until now is basically shown you the most general way of looking at it, which can be sometimes boring. We will go to the specific examples soon to make it much more easier, but as of now let us just complete the different steps. So, finally, when we reach step 5, we are going to compute the greatest common divisor GCD for this particular step that we just found out from earlier step, and the answer of that is going to be our solution. Okay. So, in operational principles there are 5 steps, but as you can see only step 2 was our quantum step. The first step once again was the choosing of a random integer, which did not require any quantum computer, except that when we chose we had to make sure that they are co-prime. Second was to make sure that we get the quantum computational part to go properly to find the unknown period of the function. So, this is the only QC part. Okay. So, first step non QC. Third step again, once we have found that, is to continue by principles which are again classical computation wise. So, for instance, we just noted whether our solution was of one kind or the other, and then we computed whether the mod values of them in a certain form or the other could let us go back to the first step, essentially indicating trivial solution, or going to the forward step where we finally computed the greatest common divisor to exit with the right answer. So, that is the basic principle of the Shor's algorithm. Now, here is the classical part, which is the order finding algorithm. In this, given x and n, where x is less than n and the greatest common divisor of the two is 1, ensures that you are getting co-prime numbers, right. The order of x is such that the least positive integer r, such that r to the power x to the power r is equal to 1 mod of n. So, classical parts include the 4 steps except step 2, as I mentioned earlier. So, the classical part consists of a random number a, which is less than n, which is picked. We compute a of n. This may be done using the Euclidean algorithms. In the Euclidean algorithm, then we find the GCD, and if it is 1, if it is not equal to 1, then it is a non-trivial factor, which is essentially, as we said, 1. We do not use that, we go back. Otherwise, we go forward, compute this to find the value of r, and if r is 1, once again we go back to 1, because that is not going to make us go any further. However, if it is not that, then we continue and we get, if r is odd, we get back to step 1, because we have to redo the problem again. If it is minus 1 mod of 1, again we go back to step 1. So, these two all of these 3 goes back to step 1. Only 4 is the one where we can do and get to the point where we can get a 7th step, where we can get the non-trivial factor of n. So, that is these are the important classical steps that we have to do in this process. So, first we are using the important result from the number theory, where we are converting into the periodic functional problem. So, here is an example that we first take. Let us take the case where my number is 15, although this is a trivial problem, but let us see if we can understand the problem. So, I am going to choose 15, which we are going to do factorization. So, let us choose the number that we said has to be co-prime with respect to the original number. So, if we take 7, x is equal to 7, what do we get? So, x to the power r mod of that number, as we discussed, are the numbers that we are looking for. So, r can be any number. So, we are going through these numbers. R can be any number less than 7. Okay. So, 7 to the power 0 mod 15, 1 to the power 1 mod 15, and so on and so forth. We see that it starts repeating after the number 3. Okay. 0, 1, 2, 3, then it starts repeating. 4 is again 1, again it goes through the circle. So, this we could look at in a classical way for a small trivial number, but what we are trying to look for is to figure out how this order finding can be done when we do it in a quantum way. So, let us choose a power of 2. Let us say q is equal to 2 to the power l, such that this q lies in between n squared and 2n squared. And if we consider f is restricted to the set, so our set that we are looking for restricted to the set where it goes between 0 and q minus 1, such that our function is given by this normalized value with respect to omega x y, where omega is the part which will give us the period. So, exponential 2 to the power pi I over q is the way how you look at the period, and that is our qth root of unity. So, this is a more generalized way of looking into the problem as to how we are going to do the order finding. Okay. So, in the classical way we just looked at it last time, we can do it step by step and we can see how it starts repeating. Now, that is possible when numbers are small, we are looking at simple solutions. However, when we look at harder more difficult cases, we can actually formulate a process, and this is the how you can actually formulate. You can use the phase of the problem in terms of quantum system to get your solution. That is the idea here. So, in what Shor was able to recognize is that in order to factor an odd integer n, let us choose for example 15, you have to go through these steps in this particular way which we discuss here. The algorithm takes this form which is perhaps able to understand. So, we have to choose an integer q such that now q such that it lies in between n squared and 2n squared, that is what we said. So, it can be any number, let us pick up 256 because it is 2 to the power something. We choose a random number x such that the GCD of x n is 1. So, we can pick a number like 7 which we did earlier. Create 2 quantum registers. These registers must also be entangled. Okay. Now, we have discussed about entanglement before, and that is the part which is critical in Shor's algorithm. We will again revisit that in slightly more detail later on, but for now just look up your notes or previous lectures to go back to understanding what entanglement is. So, these registers have to be entangled, so that the collapse of the input register corresponds to the collapse of the output register. Right? I mean, this is the criticality of entanglement, that one process essentially ensures that the other one is also correlated one way or the other. The input register therefore must contain enough qubits to represent numbers as large as q to the q minus 1, that is up to 255 in this particular case. So, we need 8 qubits, 2 to the power 3 qubits, which can give us up to 255. So, we need the input register to contain enough qubits to represent numbers as large as q to the power as large as q minus 1, which is up to 255. So, that we need 8 qubits, since 2 to the power 8 is 256, and therefore, we choose the number of qubits as 8. The output register again must contain enough qubits to represent numbers as large as n minus 1 up to 14. So, we basically need 4 qubits. S to the power 4 is good enough to go up to 128. That is more than what we need. Now, in order to look at the problem of order finding, quantum order finding, let us now go back and look at how the states can be set up. So, let us set up the states 0 and 1 in register 1 and register 2, which is our initial state. We create a superposition, that is, we apply Fourier transform to register 1. Now, this principle of Fourier transform is something which is perhaps known to you from previous studies, but if not, we have a separate lecture where we will be focusing on Fourier transform and the quantum Fourier transform principles. However, it comes under the basics of the mathematical formulations that we have been mentioning before. So, we can look back onto that once again if necessary. So, once you apply the Fourier transform argument, then what you will have is, you will have this entire state which would look like this, and then we can apply the unitary transformation to the register 2, which is u of f to register 2, which takes it to this functional f starting instead of the 1 function. Okay, so, this is our unitary function which puts in the f of x there. So, once we get this form, then we can actually apply the Fourier transform again to register 1, which is x, and we are going to get this as our Fourier transformed argument as a result of application of the Fourier transform. We make a measurement on the first register now, which gives us the value of y, because that is the part which we have now gotten into. We find the period p by using the continued fraction method for y over 2 to the power l. So, these are the 6 steps which we have just discussed for your quantum part of the algorithm. So, let me actually reiterate once before we close this lecture. So, what did we do? We basically said that we take up a trivial case where we apply from the number theory principle the periodic function principle, and we found out that it was possible to find out a value of 7, which is co-prime with 15, which is the number we are trying to find out the factors for. And for this particular kind of a case where we can do each and every number in terms of finding x to the power a mod n, we can find the periodicity by hand, because this is easy. But this gives you the idea as to how we will be setting this up, this problem up in the quantum form. So, in the quantum form, what we did was we chose the numbers and the registers in such a way so that we can set up the order finding problem. We chose in terms of powers of 2, because that is how the quantum is supposed to be. We set these functions in the sets which had the registers in those connections, and we applied our functions such that we got the period function coming out, and that was possible because of the application of Fourier arguments, where the phase of the problem comes into the picture, and we got the qth root of unity, for instance the omega value here, and we went through the individual steps in particular when we did this particular example of n equal to 15 the quantum way. Okay. So, once again even in this quantum way we had steps which did not need quantum concept, however, because it needed entanglement. Classical concepts here mathematically, the moment we have actually used qubits, we cannot really start measuring at every step. So, it remains quantum in that sense, and so we have to choose our number of registers, the number of qubits in a very important way, and that is what we have done here, and we have shown how this particularly it will look like in its final step of which register to use and which part to apply the transforms to, and what are the final results that we will be getting when we apply our Fourier transforms to the final result, so that we can finally find the period by using the continued fractions approach. With this, I am going to end the class today, because we have gone through a lot of concepts and we are going to revisit parts of it to make sure that you understand it more as we go ahead with this particular approach of algorithms. Thank you.